Hello everyone! In today's video, we are going to dive deep into an important topic in theoretical physics, which is spontaneous symmetry breaking and its connection to Goldstone excitations. So we'll break down both the maths and the physical intuition behind this theory. To start with, let's talk about what happens when a global continuous symmetry of a system is spontaneously broken. So according to Goldstone's theorem, this breaking introduces new massless excitations in the spectrum, which is what we call Goldstone bosons. In physical terms, this spontaneous symmetry breaking results in excitations that don't require any energy to move slightly around that chosen point. For example, you must have seen the Mexican hat potential. So this is a particle. It moves either in this or this direction. It doesn't require any energy to move around in whatever direction it chooses, and this is what we call our massless Goldstone bosons. Let's derive this mathematically, and we derive this using something what we call is Ward identity. So Ward identity, this thing over here, this is a very special equation in quantum field theory and conformal field theory, because it relates symmetries and conservation laws in field theories. So you look at this Ward identity, it has current in it and it has a field phi of y in it as shown. So to begin with, we'll Fourier transform this LHS and RHS of the equation. So taking the Fourier transform will essentially help us look at the behavior of the system in momentum space. I'll as proceed. So we take the Fourier transform, we add this e to the IPX thing, and even here we do the same thing. And now once we do that, in the next step what I'm doing is I'm integrating by parts on LHS. So you see this d mu term, I'm essentially bringing it out here, that's why I get a minus sign here in the next step. And if I differentiate d mu e to the IPX, first I get a minus sign, and once you do the differentiation, you'll obviously have I come out and you'll have p mu come out. That's what I get in this next step. And on the right hand side of the equation, you'll realize that, oh, we have a delta function here, and you're integrating it in d dimensions with x, with respect to x. But if you set x equals y for this delta function, obviously you're going to get 1, because if you have d dx, delta d x equals y, and if x minus y, and if x equals y, you obviously would get 1 as your answer. So the green bit integrates to 1, so you're just left with this term from here. And then after we did all this integral, reducing the delta function, look at both sides of the equation. You have everything in terms of y's, x, right? You wanna transform it to momentum space. For that, you need to realize that we can just use the Fourier transform of the current. So look at current in terms of momentum space. That is exactly the integral of d dx e to the IPX. So that's just the Fourier transform of current. And realize we already have this on the left hand side. So we already have components here. Hence, we see this is the same thing. Hence, we can transform this equation, this part of the equation, as this. We can just rewrite it, right? That's what I'm doing in the next step. I'm rewriting all that integral as current in terms of momentum space. Before that, just for brevity, we got rid of this i's. Okay, moving on. So you realized, yeah, we turned this into momentum space, and this is exactly the same. RHS is exactly the same. Now, we still have y's in our equation, right? We want to write everything in terms of momentum space. So our trick is to integrate both sides over y. So this would get rid of our spatial dependence in the equation. We do that. We get, so for the LHS, we get minus p. This is just by the definition, by Fourier transform again. If you do the maths out, if you do the math, you would get minus p here. and so essentially all weird. Okay, I think it's worth getting into how I really got into this step. So just quickly, I'm gonna gloss over it just to give you an intuition. So I had e to the minus IPY and e to the IPY. This obviously cancels and this goes away. You're left with this on LHS and RHS. And now I wanna write this as P mu JA. It's the other way around. J mu A P. And I want to bring this inside the integral. Inside the correlation function, sorry. Integral inside the correlation function. IPY. My bad. This is a y. Phi of y. So the beautiful thing here is this integral over y with e to the I minus py, phi of y, essentially picks out the Fourier transform of phi at momentum minus p. So all I'm left with is phi of minus p on the LHS, and on the RHS it's literally the same thing copied over, phi of y. So that's that. So now I've resolved how I got this part of the equation. And for the RHS, looking at this bit over here, this is just the integral over all spacetime points of the transformation dA phi of y, this bit, right? This integral corresponds to the Fourier transform of dA phi of y at zero momentum, because integrating over all y in position space is equivalent to setting the momentum to zero in Fourier space. That's all we did. That's how we got zero momentum, p is equal to 0 in the Fourier space. So that's why, so I was struggling to understand this earlier as well, why is p is equal to 0. So it's literally because we integrated over the y's. Now moving on, this term over here, the stuff highlighted in blue, is really important because this is called the order parameter, which characterizes all the phases of the theory. And if the order parameter is equal to 0, then you have a symmetric phase, and if it's non-zero, then you have spontaneous symmetry breaking, so that's a broken phase. So I also have picture over here. So unbroken phase where your order parameter is 0, and here when it's, so in other words, this order parameter d delta phi where p equals 0 acts as an indicator of symmetry breaking. When it's non-zero, it signifies that the system has chosen a specific direction, either this direction or this direction, for breaking the original symmetry. And in this broken phase, the correlation function, the original thing which we had over here from Ward identity, this correlation function must have a pole at zero momentum, right? Because when we say it has a pole, we only have a pole if p equals 0, right? So when p equals 0, we have a pole in here. And remember, we said that momentum is 0. That's what we're doing here. And this in turn signals the presence of massless excitations in the system, massless physical excitations. Now remember in QFT, you must have seen this. You always have p square minus m square. Here it's massless, so this term just goes to 0 anyway. So the massless pole signals the excitation does not carry a mass, as in that is our Goldstone boson, right? So physically it tells us these excitations also require no energy to be excited at long wavelengths. This is why they're massless, so there's no cost associated with these small oscillations. No cost associated with either it oscillates here or there, we don't know. It chooses a direction and there's no such cost associated with it. So this pole, essentially this pole here, it represents the massless nature of Goldstone bosons. And that would be it for now. So in summary, we saw spontaneous symmetry breaking leads to massless excitations known as Goldstone bosons, as shown through the mathematics of word identity and Fourier transform. This concept not only deepens our understanding of symmetry in physics but also plays a foundational role in many physics, from particle physics to condensed matter physics. Thank you for watching this, and if you enjoyed this explanation, please don't forget to like, subscribe, and hit that notification bell for deep dives into theoretical physics. Thank you.